Our paper studies the application of a multi-directional thrust multi-rotor design for physical interactions with the environment. In particular, this work paves the way for the use of such aerial robots as flying assistants. The main contribution to this paper is the realization of a new aerial robot, the OTHex, targeted for bar lifting operations. This contribution is twofold. First, a novel design of an aerial robot is proposed based on our previous experience, and second, a control architecture for this aerial robot is proposed, allowing both fine trajectory control and also compliant force control. The OTHex is a novel design of a multi-directional thrust multi-rotor. Its name is derived from its design features. O stands for open, as there is an aperture between the frontal propellers for object pass-through. T stands for tilted, as the propellers are non-collinear to ensure the multi-directional thrustability. Hex stands for hexarotor, as the flying platform is equipped with 6 propellers. The robot arm is mounted via a 1 degree of freedom passive revolute joint to the flying platform. The proposed control architecture aims at allowing both precise position control and compliant force interaction with the environment. It relies on precise velocity control of the propeller spinning rate, which is commanded by a full pose controller. In order to enable safe and robust physical interaction, we designed an admittance filter which relies on a momentum-based wrench observer. The experimental results consist of both the successful realization of an OTHex prototype and the validation of both the design and control strategy via experiments. The validation is conducted to assess the performance of the system in the nominal case and also to assess its robustness to both parameter uncertainty and external force disturbances. The nominal experiment consists in flying to the bar and lifting it. This mimics, for example, gutter installation or structure assembly. It can be separated into 4 sequences: the approach, the grasping, the lifting, and the holding of the bar vertical. The first robustness experiment aims at assessing the system's ability to handle parameter uncertainty. In this case, we provided the planner with a nominal grasping point, the red circle, offset 20 centimeters with respect to the real grasping point. Despite this large discrepancy, the system performs well and is able to lift the bar in a smooth manner. The second robustness experiment aims at assessing the system's robustness to unexpected force disturbances. In this case, we tied a rope to the bar to block its ascent. Once the wrench observer detects an external force exceeding a certain threshold, the planner reacts in order to ensure the stable behavior of the system, leading to a compliant reaction. Without the compliance induced by the admittance filter, a crash would have most certainly occurred. To conclude, in this paper we proposed an original design for an aerial robot, the OTHex, tailored to the task of lifting bars. We developed a compliant control framework necessary for the safe physical interactions. We conducted successful bar lifting tests with our OTHex prototype and also exhibited robustness to force perturbations and parameter uncertainties. Thanks to its compliance, the OTHex could be used as a flying assistant for ground robots or human operations in construction tasks involving long bars.